Look at the beautiful topic I bring you today. In the playlist we are diving into a fascinating world, the gravitational field. Before we begin, I'd like to encourage you to approach it with a bit of affection and fascination. Humans are the only species capable of looking at the sky and marveling at what's out there. Since the beginning of our history, we've tried to explain it, sometimes more accurately than others. But what makes us unique is the very act of trying and continuing to try even today. Perhaps seeking answers to what the universe is could also help us understand who we are and the meaning of our existence on this small rock flung into the universe called planet Earth. But today we are not diving into metaphysics, we are sticking to physics. We are going to stand on the shoulders of Kepler and Newton in order to precisely explain the gravitational phenomena within the garden of our home, the solar system. So, fasten your seatbelt because we are about to embark on the gravitational field.
Binnacle project.
The first thing I bring is this formula sheet with all the equations we'll use. You can download it from the link I've included in the description. I don't want to repeat all the theory that your teacher has probably explained. Instead, I want to provide you with an eagle's eye view so you can understand what we'll tackle in the upcoming videos. And to make sure you don't get bored, we'll work through small exercises where you'll see every little formula of the sheet in action. So, grab some paper, a pencil, a calculator, because we are diving into this fascinating topic. Let's start with this simple question. It says, calculate the gravitational field at the distance of 5 meters from a point mass of 80 kilograms. Let me try the situation for you. They are saying that we have this 80 kilograms mass, 80 kilograms, imagine a person, and they are asking to calculate the gravitational field 5 meters far from the center of this mass, okay? This is 5 meters. So let's call it point P. The first thing you must understand is that even though there is no mass at this point, there is no mass, automatically there is a gravitational field because of the existence of this other mass. Let's call it creating mass, okay? Even though there is no mass, here there is no force, there is no gravitational force, but you can find here a gravitational field represented by this vector. The gravitational field is always attractive, so that's why it's pointing to the creating mass. And this is the expression that we are using. Gravitational field equals negative g multiplying creating mass and divided by the square of the distance. Two little but very important formalities. As the gravitational field is a vector, it is necessary to place here the unity vector in order to convert this part of the equation also in a vector. The unity vector is this one. It's a little vector pointing to the outside. And as the gravitational field is always attractive, that's why we're placing here this sign, okay? These two formalities are very important, so please don't forget them. Don't worry about these formalities, you'll quickly get familiar with them. And now it's time to use our calculator to do negative. This is the universal gravitational constant, which value is 6.67 multiplying 10 to the negative 11. Now the creating mass, 80 kilograms, divided by the square of the distance, 5 squared. This is the unit vector, and please use your calculator to do negative 6.67 multiplying 10 to the negative 11, multiplying 80 and divided by 25. Are you getting negative 2.13 multiplying 10 to the negative 10? And this is a vector, so don't forget it. And the most important thing, the units. Newtons per kilogram or meters per second to the square. And that's it. Don't forget what we've done. For the simple fact of existing a creating mass, automatically appears a gravitational field all around it. And at this point P, for example, where there is no secondary mass, what does really exist is a gravitational field, and this is its value. In the same way as at this point that I'm indicating with my finger, There is no mass, so there is no force. But what we can find here is a gravitational field created by the mass that is under my feet. And the best proof that there is a gravitational field is, look at what happens when I'm placing a mass at this point. It falls.
Binnacle Project.
The second magnitude that I want to introduce is the gravitational potential. Look, using the formula, calculate the gravitational potential at that point. I bring you this new magnitude, the gravitational potential, please not to be confused with gravitational potential energy, okay? Only gravitational potential. And this is the formula we are using. Negative g multiplying the creating mass and divided only by the distance. Not to the square of the distance, only the distance, okay? And its units is joules per kilogram. And the good news is that this magnitude is not a vector, so we won't have to deal with vector-related issues. This is a scalar, so let's calculate it and I'm going to explain what it means. We are introducing negative 6.67 times 10 to the negative 11, multiplying 80, and divided only by 5, not 5 squared, only 5. If we use your calculator, please follow me. Negative 6.67 times 10 to the negative 11, multiplying 80 and divided by 5. We are obtaining a potential of negative 1.07 times 10 to the negative 9 joules per kilogram. And that's it. And what does this magnitude mean? What does this number mean? It means the work done by this mass to move 1 kilogram of mass from point P to the infinity. Okay, I repeat. This is the work done by this mass to move 1 kilogram of mass from this point to the infinity. And as it is negative, what does this sign mean? It means that this is a work that must be done by you, not by this mass. This mass wants to attract our kilogram, so if you want to move it to the infinity instead, this work must be done by you. Don't worry about these ideas, let them mature because we will return to them soon.
Binnacle Project.
And now it's time to finally place a little mass at point P to see what happens with it. Look, if a 2 kilograms mass is placed at the previous point, calculate the gravitational force that it experiences. Look, we're placing here a second mass of 2 kilograms. 2 kilograms, okay? So this little mass is going to experience a force due to the presence of this other one. And here you have it. This is the force, the vector force that it is going to experience. And this is the formula that we are going to use. The force, as it is a vector, please don't forget this little sign, equals negative g multiplying the big mass, the little one, divided by the square of the distance again. And units, newtons. And as this must be a vector, don't forget to place here the unit vector. You are now looking at the crown jewel of this topic and possibly one of the most important jewels of science. Newton's discovery of this formula and all its implications helped end centuries of superstition and ignorance, propelling humanity toward new horizons. If through this video I can inspire even a small spark of excitement in you to discover new things to make the world a better place, I would consider my job more than done. Having said that, let's calculate our force. It's negative 6.67 times 10 to the negative 11, multiplying the creating mass, 80 kilograms, multiplying the suffering mass, our 2 kilograms, divided by the distance to the square. Let's use our calculator and we are obtaining negative 6.67 times to the negative 11, multiplying 80, multiplying 2 and divided by 25, and we are obtaining negative 4.27 approximately times 10 to the negative 10 unity vector and in newtons. Okay? And one last little detail. Look at what I am rounding. This is the formula for calculating the gravitational field. So we can also calculate the force by using our suffering mass multiplying the gravitational field. So if we do 2 kilograms multiplying negative 2.13 times 10 to the negative 10, you can use your calculator in order to obtain the force. And that's it.
Binnacle project.
Now that we've placed this little 2 kilograms mass at point P, let me show you another magnitude that appears only when there is a little suffering mass. I'm talking about the gravitational potential energy. Look, section D says, using the formula, calculate its gravitational potential energy. And this is the formula. The gravitational potential energy equals negative G multiplying creating mass, suffering mass, divided by the distance. Not distance squared, only the distance. And units, joules. This is the gravitational potential energy, not to be confused with the gravitational potential. Okay? Now let's use our calculator to do gravitational potential energy equals negative 6.67 times 10 to the negative 11 multiplying 80 kilograms, multiplying 2 kilograms and divided by 5. And we are obtaining negative 6.67 times 10 to the negative 11 multiplying 80, 2 and 5. And we obtain negative 2.13 times 10 to the negative 9 joules. And now let me show you what does it mean. The gravitational potential energy is the work done by the creating mass to move this little mass from point P to the infinity, okay? It's the work done by this mass to move the little one from point P to the infinity. And as you probably know, it is a work that must be done by you because the field will try to attract this mass instead of moving it to the infinity. This is a work that must be done by you, so that's why it's negative. And that's it. Before moving on to the next section, let me tell you one little thing. This part of the formula that I'm rounding is precisely the gravitational potential. So we can also calculate the gravitational potential energy just multiplying the suffering mass times the gravitational potential. And if you use your calculator to do 2 kilograms multiplying negative 1.07 times 10 to the negative 9, you surely will be obtaining this result. Don't forget it.
Binnacle project.
In this new section, we are going to aim high, literally, because we are calculating the gravitational field at 450 kilometers above the Earth's surface. Look, this is the situation. This is our planet. And this is its radius. And at 450 kilometers above the Earth's surface, point P, we are calculating the gravitational field. There is no mass here, so there is no force. But what really exists is a gravitational field that we are representing by this little vector. And the formula that we are using is this one. The gravitational field equals negative G multiplying the creating mass, in this occasion is the mass of our planet, divided by the distance squared. That is the radius of our planet plus the altitude of our satellite, of our point, but squared, okay? Don't forget the unit vector and the units of this magnitude, that is newtons per kilogram. And now let's use our calculator. If you substitute the numerical values, you will obtain negative 8.56 newtons per kilogram. Please be careful with placing the distances in meters. Don't forget to square, and here is the result.
Binnacle project.
The next section is asking us to calculate the other magnitude that we can calculate at points where there is no mass, like the gravitational potential. And we are using the formula that you already know. The gravitational potential equals negative the universal gravitational constant, multiplying the creating mass, that is the mass of our planet, divided by the distance, the radius of our planet, plus the altitude. Don't forget, please, to place these magnitudes in meters. That is 450 times 10 cubed meters. Okay? So now let's use our calculator. Hope you've obtained negative 5.84 times 10 to the 7. And let me tell you, what does it mean? This is the work done by our planet to move a 1 kilogram mass, from point P to the infinity. And as this is a work that must be done by you, not by the planet, because the planet wants to attract the mass. This is a work that must be done by you. That's why it's negative. Okay? So don't forget the definition of gravitational potential.
Binnacle project.
Now they're telling us that they are placing a 150 kilograms mass at point P. This is a 150 kilograms mass at this point. So now automatically appears a force. There is a force attracting to the Earth. There you have it. And what are we going to use? For Newton's formula. That is negative g multiplying the creating mass, multiplying the suffering mass, divided by the distance, but squared. This is the distance, the radius of our planet, plus the altitude, but squared. Don't forget to place here the unit vector and also the units of this magnitude, newtons. And now it's time to use our calculator. Hope you obtained negative 1284.17 newtons. It's negative because it's attractive, okay? But as you can see from the part of this formula that I'm rounding, this is the gravitational field. This is the gravitational field. So we can also calculate the gravitational force just by multiplying the suffering mass times the gravitational field. And if you use your calculator to do 150 times negative 8.56, you will also obtain negative 1284, and don't forget the unit vector, newtons, okay? And this is another way of doing this calculation.
Binnacle project.
The next section says, calculate the tangential velocity required for it to remain in circular orbit. And look, this is the situation. This is our planet, and this is our satellite. But if our satellite doesn't have velocity, it would fall back again to the Earth. So what can we do? We can apply a velocity for it to remain here in a circular orbit, okay? And for this situation to happen, two forces must be equal in magnitude but opposite in directions. These two forces are the centripetal force, which pulls it inward, and the centrifugal force, which pulls it outward, okay? And by the way, the centripetal force is Newton's force. Newton's force. So let's do it. Newton's force must be equal to the centrifugal force. Now let's place properly the formulas, but in magnitude. Newton's force, g multiplying the mass of our planet, multiplying the mass of our satellite divided by the square of the distance, must be equal to the centrifugal force, that is, the mass of the satellite multiplying the square of the velocity divided by the distance. And you can see that the mass of the satellite cancels out as one of the distances. And now we can solve for the speed. The velocity of our satellite must be then equal to the square root of g multiplying the mass of our planet divided by the distance. This is the distance we are introducing in this formula, that is the radius of our planet plus the altitude, okay? Radius of the planet plus the altitude. And now let's use our calculator to do 6.67 times 10 to the negative 11, multiplying the mass of the Earth, 5.97 times 10 to the 24, divided by the radius and the altitude, but in meters, okay? So we are placing these values, but in meters, and a square root. We are obtaining 7,641 kilometers per second. This way, our satellite will not fall to the Earth.
Binnacle project.
In the next section, we are asked to calculate its mechanical energy. Now that we have our satellite orbiting the Earth, it contains mechanical energy, and it's very easy. As our satellite contains velocity, it contains kinetic energy. But also, as our satellite is placed next to a very big mass, it also contains potential energy. And we are just placing the formulas, and we have 1/2 times the mass of our satellite multiplying the square of the velocity. And potential energy, negative g, multiplying the mass of the planet, the mass of our satellite, divided by the distance. And now it's time to use our calculator, and that's it. Hope you obtained negative 4.38 times 10 to the 9 joules. And don't forget what we've done in these sections. First of all, we've calculated the force, the gravitational force that this satellite is suffering. Secondly, we calculate the necessary velocity applied, tangential velocity, for it to stay in this circular orbit. And finally, as our satellite has speed, it has kinetic energy. But also, as it is quite near to a very big mass, it also contains potential energy. And that's it.
Binnacle project.
And now it's time to be brave and calculate the gravitational potential not by using the formula, but using the procedure you're about to see, using the integral. And please don't be scared, because I know that mathematical treatment is always hard, but this is not difficult at all. It is very easy and very mechanic. Look, this is a situation. Let's suppose that this is our planet, this is the sun or whatever, and we are asked to calculate the gravitational potential at this point, let's say point P, at d meters from the center of this planet. Can you remember the definition of gravitational potential? It is the work done by our planet to move 1 kilogram of mass from point P to the infinity. Don't forget it. It is the work done by our planet to move 1 kilogram of mass from point P to the infinity. So this is the path we are traveling to move to the infinity. And this is our mass, 1 kilogram. We are moving from point P to the infinity. We are placing also the Newton force. This is the gravitational force that tries to pull back the mass to this planet. And we are placing also the differential displacement vector that we are pointing to the infinity because we are traveling towards it. Okay? First step, easy, right? Now we are calculating the work done by our mass to move our kilogram from point P to the infinity. And we are placing the force, scalar the displacement. And can you remember the definition of scalar product? Here you have it. Integral from point P to the infinity. The magnitude of the first one, the magnitude of the second one, multiplied by the cosine of the angle between them. And there you can see that we have 180 degrees. And if you use your calculator, you can see that the cosine of 180 is -1. So that's why I'm placing this -1 here. Integral between P and the infinite. And now I'm placing the force, the Newton force, that is the universal constant gravity, the mass of the planet, 1 kilogram divided by the distance. And the distance at this moment is r. Okay? R. But r squared, as Newton says. And the displacement vector. Second step, easy, right? And now it's time to solve the integral. I'm taking out these two constants. -g, the mass of the planet, the integral between P and infinite, and I'm rewriting 1 divided by r squared like r to the -2. And can you remember, it's very easy, that gm, the integral of r to the -2 is r to the -1 divided by -1, okay? Between P and the infinite. These two minus signs can cancels out, and we have g multiplying m, and r to the -1, I'm writing it like 1 divided by r between P and the infinite. And now it's time to place the infinite and the point P. G, m, 1 divided by infinite minus 1 divided by the distance to point P, that is d. And 1 divided by infinite is 0, and there you have it. The potential at point P is -g m divided by d. Okay? Use the same that you can see here. So don't forget what we've done. The set is very simple, it's very easy. We just place this big mass and point P, and our little mass, 1 kilogram of mass, moving from point P to the infinite. And look at the vectors we've placed. Newton's force pulling back and displacement vector. The angle between them is 180. And then we've placed properly the definition of work. Don't forget that the cosine of 180 is -1, and then we slowly solved the integral. That's the way.
Binnacle project.
In this video, I wanted to provide you with this gravitational field formula sheet and introduce you to some procedures that we are using in the next videos of this playlist. By the end, you will have a solid understanding of this topic, but beyond that, I want you to approach it with enthusiasm, because it is a fascinating topic that involves how bodies move around us. It shows that there is no hand of a God behind, but rather that bodies follow physical laws that we can access through mathematics. So, I hope you enjoyed the journey. See you in the next video. And now, watch a theory video if you think you've gotten lost in some aspects, or skip to the next exercise to continue climbing. And as always, like, turn on notifications and comment. See you soon!